back. Today we're looking at unique paths, number 62. There's a robot on an M by N grid. The robot is initially located at the top left corner, grid 0, 0. The robot tries to move to the bottom right corner, so grid M equals -1 and N -1. The robot can only move either down or right at any point in time. Return the two integers M and N, or given the two integers M and N, return the number of possible unique paths that a robot can take to reach the bottom right corner. The test cases are generated so that answer will be less than or equal to. Okay, so let's think about this. So let's say there's a starting point and I guess a finishing point. And the starting point you have a little robot guy. And you need to walk to this star, right? You can only go down and you can only go right. So you can go down, I guess, as many times as you want and right as many times as you want. So let's take, for example, this path, right? This path right here that I just drawn, that's one unique path. Okay, it's a single unique path. And um, so there's only down and there's right. So there's no left, there's no up. So we have no risk of going back up the path, right? So we don't have to check for that type of um, visited scenario. There's only down and right. So let's think through what makes a unique path. If I go right here, there's only one way to go right here. There's only one way to go down here, right? And if I go, let's say my first move is right, there's still only one way to go here, only one way to go here, only one way to go here. So all the way down here, that's still a single unique path. If I go down here, that's still a single unique path, right? And what path is that? That's a right, 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 down, down, right? So if I wanted to create some type of list of all the moves in this path, it would be this, right? And then what else do I have available, right? I have this type of, what if I went down first, right? I went down, I still did all the rights, and then I did another down, right? So this is another unique path. And what if I did two downs first, right? I did these two downs first, and then I did all of these rights, and that's a unique path, right? And what if I did the downs that are in between here, all unique paths, right? So if I'm given this grid, what I could do is do something recursively where I append to this path, right? And I wrote this code up here, and the code is gone. Let me try to find it. The code. Okay, I guess I don't have the code, but you can imagine, um, we have some type of matrix, we have some type of um, go function. The go function takes a row and a column and a path, right? And then that go function is called at the beginning stages, right? 0, 0, and the path is an empty array. And then what we're doing is we're adding to the path, right? Here I would do something like check out of bounds. I would check for the base case, and the base case would be something like if the length of path equals the target length, then push it to some results array, right? Results equals this. So then I do results append path.copy, right? So that's what would happen if I get to that base case. And if there's no base case yet, then I traverse, right? Otherwise, traverse. And the traversal would be calling the go function. This one would go down, right? And then the path would be, adding the value that's here, right? Um, and this is one of the options, right? Instead of +1 on the on the row, it would be +1 on the column, right? And this would be one of the options. This type of recursive version of it, where I would build these paths up. Now, that completely works as a program, right? What we would do at the end of this is we would return the length of results. Um, Now, what's the problem here? The code works. The problem is the runtime. So what's going to happen here is I'm recursively going to every step, and um, you know, down and right will be two options. And then how many ways can I do this? The length of n plus n. So it's going to be 2 to the power of n plus n, right? So the runtime here um, will be 2 to the power of n plus m. Space here won't matter, but you know it'll basically be that space. Now, can we do this with dynamic programming? Now that takes a different type of insight, right? So what would mean that we do this with dynamic programming? Well, the board actually is naturally, we got very lucky here. It's naturally it's a 2D table essentially, right? So let me try to, what's a fast way to delete this? I guess I just have to delete it one by one. It's terrible. I wish AI could do this part. Um, but let's talk to it. So we naturally have this 2D table, right? And we put some of the ones here, right? And that actually gives us information. So there's only one way to go down completely, right? 1, 1, 1, 1, 1. There's only one way to go down completely. There's only one way to go right completely, right? There's only one unique path, right? And that means that your path is going to start off, right, something like right, 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 right. There's no way to do a down, right, left, down, up, left. There's no way, right? So here, let me delete this little computer guy as well. There's only one way to be at the origin. So the question that we have then is how many ways, as our goal, can we get to this endpoint, right? And we can do that by filling this table if we can answer one thing. How many ways can we get to this point? And is there anything in the table that helps us, right? We know this is unique and this is unique. Well, how many ways is it possible to get to here? Well, we can go right once. We can go down once. We can go down once. We can go right once. So actually, to get here, it's the addition of this one and this one, right? That's a 2. Now what about right here? How many ways can we get to this point? Well, we can go right, right, down, okay? And then actually from this point, there's only 2 ways to get to this point. From the here, there's only one way to get to here. So it's 2 plus 1, right? It's this 3 right here. And how many ways can we get to here? It's this, this, and it's all the way down, right? So it's all the way down, every single square, actually until we reach this point right here, right? So if you had to add it up, this would be 4, 5, 6, 7, and then this would be 3, 6, 10, 15, 21, 28. The answer would be 28. There's 28 ways to get down to this point right here. Okay, so now that we have the general structure, let's think about this in code. What does this look like, right? We have this, I'll call it DP for dynamic programming. We have this table, but we don't have it yet. Let's create this table, and we can, we can start it off as zeros or empty. Doesn't matter. We start off as 0. All right. So how many rows are here? Which one's a row and which one is a column? The rows are, it actually doesn't even matter which ones are the rows or which ones are the columns, but I'll just do it here so it's so we can visualize it. Um, so DP, we want number of columns, right? So just in case you don't know what this does, this is going to take the value 0. This is going to take the value 0 and make, depending on the number of columns, make that much of it and return that single array, right? And how many times do we want to do that? We want to do this for the number of rows that exist. And if we make this a list comprehension, we'll have a list of lists, right? So if we return DP, we'll have this list of lists of all the zeros that we want. Okay, perfect. So first things first, the first row, the first column, they're all going to be ones, right? So let's just iterate through that and make sure it works. So for I in number of columns, that's going to be the range, right? DP at the 0 row for each one of these columns is going to be 1, right? Let's just take a look at what that is, right? So for the first row, we're going to make that all ones, right? Because that's what it is here. Okay, let's do that for the column. So for I in range n rows, for that first column, we're going to make that 1, right? So the first element here should all be ones. Perfect, right? So let's do the iteration. So for I in range, so for each one of the rows, we want to do some type of iteration. For each one of the columns, we want to do some type of iteration. And we're actually going to start at 1. We're not going to start at 0 because the 0 is already filled out, right? So we want to start at this point, right? We want to start at 1, 1, and we want to go until, right, first row still, 1, and then n calls, right? And n calls here is going to be number of columns, which is 7. So we want to go all the way to 7, exclusive, because this is Python. We're going to go to 1, 6, right? So here would be 1, 6, right? So 1, 2, 3, 4, 5, 6. These are the indices. Okay, so what is the value that goes here? It's the value above it, and it's the value to the left of it. What's the value above this, right? I'll just make it super clear. I'll say above, and that is in RDP. It is the row number minus 1 at this column. And what is to the left of it? It is this row, j minus 1, because it's the column to the left of it, right? And this point, right here, would be the value is above plus to the left, right? And we want to set that at dp I j to this value, right? I think it's clear enough, so I probably don't need this part anymore. But that's what I'm setting as a value, right? So what's dp? dp is going to be all the additions that we made in the drawing. Now, what do we actually care about? We only care about returning the element that's the last element on the last row and the last column, right? So we're actually only returning dp, number of rows minus 1, number of calls minus 1. We don't need results here. All right, and we got our number 28. Let's try it, see if it's fast enough. It's fast enough for us.